Now we start with the second video on thermodynamics, external work. Now to establish a formula for external work, we have to take into consideration a hydrostatic system. We take hydrostatic system to be a closed system. First we have to understand what is a hydrostatic system and why we are going to take hydrostatic system as a closed system. Already we have studied that a hydrostatic system, or rather a system which obeys Pascal's law, is called a hydrostatic system. If you can remember, the property is that pressure is uniform throughout the system and acts normally outwards at every point on the walls. This was the statement of the Pascal's law. Secondly, an additional pressure applied at any point gets transmitted throughout the system in such a way that the pressure everywhere continues to remain uniform. This we have studied in the hydraulic multiplication theorem, hydraulic press, hydraulic brakes. I'm not going to do, I'm not going to explain it explicitly now, but the thing that we have to say that hydrostatic system is a closed system. Why? Because these conditions of Pascal's law or the flowing of uniform pressure throughout the system are obeyed by number one, small amounts of liquids for which the effect of gravity may be neglected. They are obeyed by small amounts of liquids for which the effect of gravity may be neglected. That means we have to remember that for small amounts of liquids. Number two, we can say gaseous systems. That means number one can be, you can write here small amounts of liquids, and number two we can write gaseous system, gaseous systems. For these two, these conditions are obeyed. That means for the hydrostatic system. Now this means that however all liquids are nearly incompressible, as all liquids are nearly incompressible, any change in pressure does not produce an appreciable change in volume. Liquid is incompressible, that is why if we can change pressure, that will not produce an appreciable change in volume because it is incompressible. But for this reason only, for the thermodynamical analysis of a hydrostatic system, it is convenient to take a closed gaseous system. So hydrostatic system can be taken as a closed gaseous system. Now we have to find out the value of the hydrostatic work. Now for this we take a cylinder like this with a gas in it and a piston attached to it. Now this piston, the pressure within the gas is P and the volume is V. Now this pressure will force the piston to move outwards. Now suppose the piston we get after some time in this position, a displacement of dx. Now the volume and the pressure of the gas at the first instance was V and P. The pressure now forces the piston to move along the walls. These walls are frictionless, very much frictionless, through a small distance of dx. Now let this name be A and be B. So it moves from the position A to the position B. The displacement occurs when a slight difference develops between the pressures of the system and its surroundings. First we have to understand this thing. This displacement occurs when there is a slight difference developing between the pressures of the system and the surroundings. Surrounding means the surroundings. Now a small outward pull on the piston, a gain of a small amount of heat from the surroundings, etc., may initiate such a displacement. Now during this displacement, however small, the pressure P of the system may change. The pressure P may change, but at every instance the pressure must be uniform throughout the system. A sufficiently slow motion. Now you have to remember this thing. A sufficiently slow motion of the piston is required to satisfy this hydrostatic condition. Now I'm not going to explain it much more. You have to learn the formula first. Learn how do we find out the amount of work done in this kind of an infinitesimal process. Now if we take the work done to be dW, I'm straightforward moving into the process of work done. Now dW is equal to force into displacement. Work is equal to force into displacement. We have already studied the displacement is dx. Now what is force? Force is pressure into area into displacement was dx. So P, now alpha dx means dV. Now to explain it, we know that force is multiplied, if force is found out by the product of the pressure and the cross sectional area of the piston. Now cross sectional area into dx, that means cross sectional area into this, that means this increase in volume, or rather the change in volume. That means if we take the initial volume to be V1 and the final volume to be V2, so we can write dV as V2 minus V1. Initial volume is V1, final volume is V2. V2 is more, so subtracted part will give you dV. That means alpha dx means dV. So now this is the work for an infinitesimal process. So we can write dW is equal to pdV. Small amount of work done. Now for a finite process, this was a very small process, infinitesimally small. But for a finite process, you have to take the integration form of this integration dW, total work done, P dV, as our integration is with respect to V, so you have to take the values V1 to V2 as the lower and the upper limits. Now in this relation, when there is no change in volume, that means suppose first case dV is equal to 0. That means initial volume and the final volume is 0. Therefore, V2 is equal to V1. V2 minus V1 is equal to 0. So, V2 is equal to V1. That means the initial and the final volume are the same. Here, you will see that W is equal to 0 because dV0 means the work done is 0. So, no work is done in the process. Number 2, we can say that when the volume increases, that means dV is greater than 0. Volume increases for an expansion. When volume increases for an expansion, that is we write here for an expansion, dV is positive, more than 0. So here therefore dW is also greater than 0. We have to do a positive amount of work in this process. So a positive amount of work is done in this process. The system releases some energy to the surroundings. It is termed as work done by the system. Work done by the system. Now you have to understand these things very well. Work done by, I have underlined the word by, work done by the system. So dW is greater than 0, that means work is done by the system. Now what kind of work has been done? Positive amount of work has been done in this process, and it shows that the system releases some energy to the surroundings. I have to write it. The system releases some energy to the surroundings. That means the system here is doing work. So we have written work done by the system. Third one is volume is decreasing, dV less than 0. That means the volume is decreasing. So dW is less than 0. That means here what is kind of work? In this case number 2, it was positive work. Here it will be the complete opposite, that is negative work. That means negative work is done in this process. That means in the previous process, the system was releasing the heat. Here it will be the system will receive heat from the surroundings. Negative work, system receives heat from surroundings, so we term it as work done on the system. On, by and on. Now for an isochoric process, we will now start to discuss the types of processes that we had already discussed: isochoric, isobaric, isothermal, adiabatic. The first one is isochoric process. For an isochoric process, we have already seen that V is equal to 0. That means there is no change in volume. Therefore, dV is equal to 0 also. So, if dV is equal to 0, therefore W is also equal to 0. That means no work done. The second is if we take isobaric process. Baric means the pressure is constant. Pressure is there is or the pressure is not changing. Pressure is constant. Now we have found W to be integration of V1 to V2 P dV. That means if we take P as constant, we can take it out of the integrated form V1 V2 dV. That means this integration gives V, so it is V2 minus V1. So this is the amount of work done for isobaric process. Now the two cases that are left are isothermal and adiabatic. And expressions for isothermal work and adiabatic work for an ideal gas, we will evaluate those formulas using the ideal gas equation of state PV is equal to RT, but I will take into consideration it after I have discussed the first law of thermodynamics. But now let us move into the PV indicator diagram. PV diagram, or they are termed as indicator diagram. This is a very important part and has to be understood very well, because diagrammatical questions are asked in the competitive examinations. Pressure and volume diagram. I have drawn a diagram with the x-axis containing volume and the y-axis containing pressure. Now, what is the point? First, you have to understand what is a point. Number one case, a point is an equilibrium state. A point is an equilibrium state. Now, if we say the point to be A, let us take into consideration the point A. It represents fixed equilibrium values of P and V, because at this point the volume V has a value V1 and pressure also has a fixed value. Then following the equation of state, the temperature will also have an equilibrium value. So this expresses an equilibrium state of the system. So a point is an equilibrium state. Number two, what is a line? Number two, a line is a process. What is a line? Line is a process. Here 2 points, say A and B, represents two equilibrium states. A is a point, B is a point. So they represent two equilibrium states. So any line joining them with an arrow like 1, 2 represent the process A to B. Now I have directed the arrows from A to B for these first two lines, and the third one is B to A. So a line is a process means A to B process has been signified by or mentioned by line number 1, line number 2, as the arrows is pointing towards B from A. The same two points may be joined by different lines. This means that the different processes can be performed within the same two cases. What does line 3 means? A process that is from B to A. You have to take into consideration the direction of the arrows. As the direction of arrows is from B to A along this third line, So we have written B to A along line number 3. Now we have already found out what is the work done. Now work done, I can say work done for finite process. For finite process, that means you have to start from an initial value V1, from V1 to V2. The value of volume has changed from V1 to V2, and the expression just in the previous page I have written PDV integration of V. Now from integral calculus we know that an integral has a graphical representation. Now it can be inferred that the work done W in a process is represented by the area under the line joining the process and above V-axis in the PV diagram. For example, in this diagram, work done in the process A to B, that is area, I can name this process as 1, this process as 2, and this process 3. So I can write here work done in process A to B 1, that means along line 1. So line 1 means this one, line 1. So the area will be A1B C D. I repeat, A1B C D equal to area A1B C D. So an area in general we can write an area like this is equal to the amount of work done. Now we move into the concept of positive work and negative work. What is positive work and what is negative work? Now from this diagram we can say that the process A to B, these two processes, the area covered by these two graphs will be of a positive work. A to B by line 1 and line 2, they represent an expansion. So I write here the process A to B along 1, again A to B along the process number 2. They both represent, what they represent? They represent a expansion so work is positive. But what is negative work? From this diagram only, the process B to A, process from B to A, that means we are moving from a higher volume stage to a lower volume stage. Whenever this happens, that we are moving along the process, along the line, from a higher volume value to a lower volume value, that work is known as negative work. That means from B to A along process number 3, we can term it as a contraction. That means volume is decreasing, so work is negative. From this formula also you can do this, V2 minus V1. In this case it was V2 minus V1 because when is equal to work, it is positive when V2 greater than V1 and negative when V2 less than V1. So there will be a negative sign in front. Now representing an isochoric process in a graph. Now very easy. If this is P and this is V, we all know that isochoric process, the volume does not change, the volume remains constant. So the graph will be like this, straight line. You can name it A to B. This covers no area, hence the work done is 0. Now representing another one, representing an isobaric process. Here pressure does not change. That means the line moves like this, pressure, volume. Now if we name this as C to D, you have to point an arrow. You have also to point an arrow in this direction also. So for an isobaric process there is work done, because here from volume V1 to volume V2 we have got a difference in position of V. So P into V2 minus V1. Suppose this is V1, this is V2. Now cyclic process. Now this is a very important term. Why I say very important? First we have to understand what is a cyclic process. Now if a system after any number of individual process comes back to its initial state, that means it has started from this and comes back to from where it has started. I repeat, if a system after any number of individual process means this is one individual process, this is one process, this is one process, after comes back to the initial state, it is said to have gone through a cyclic process or simply a cycle. It is represented here by ABCA. So the cyclic process here represented is ABCA on a PV diagram, as you see. Now the initial state is equal to the final state is equal to A, not equal to, I must say equivalent. The initial state equivalent to final state equivalent to A. Now this 3 indicates the same state A. So the work done in a cycle. So we find the work done in a cycle. Now what is the cycle here? ABCA. ABCA. Work done in a cycle means WAB plus WBC plus WCA. So we can take these 3 to be individual processes. Now what is WAB? AB is AB, B dash, C dash, A dash. That means area under the curve AB means AB, B dash, C dash, A dash, A. So is equal to, this means area AB, B dash, C dash, A dash, A. Now as this is moving towards the right side, that means it is indicating an increase in volume. So this is a positive area, or rather a positive work done. But this process, that is from B to C as well as from C to A, these two processes are indicating a reverse direction. That means the direction of decreasing volume. So there will be a negative sign in front, because the work done here will be negative. So minus area of, now what is BC? We can write B, B dash, C dash, C, B, B, B dash, C dash, C, B, and one more, that is this area under the curve CA, minus area A, C, C dash, A dash, A, which leads us to the area ABCA. That means the cyclic process was ABCA. So the area under this 3 results in area ABCA. Thus the work done in a cycle is equals to area enclosed by the cycle on the PV diagram. This work is positive for a clockwise cycle like ABCA, but it is negative for an anti-clockwise cycle. So positive work for clockwise cycle, that means increase in volume, not like this, increasing volume, and negative work for anti-clockwise cycle,